So I'm just going to quickly go through the solutions to the organic chem practice problems. All right, so first, what's the functional group shown? All right, that would be a carbonyl. Remember that carbonyl just specifically refers to the C double bond O. You would see them in aldehydes, esters, ketones, anything that's got that particular part right there. All right, next one, what is the IUPAC name of this? All right, you find the longest chain, 1, 2, 3, 4, 5. That's a pentane, and the branch point would be here. That would be off the bromines off the 2. The methyl group is off the 3, so that would be 2-bromo 3-methylpentane. All right, what's the mechanism? So the key thing about this question is the absence of light. All right, if it was in the presence of light, you would most likely have radical substitution. All right, but since it's excuse me, in the with an alkene and a halogen in the absence of light, that's going to be electrophilic addition. And remember, what addition means is that the entire halogen, like a Cl2 or a Br2, if you look at the alkene and that halogen molecule, you would have all the exact sum total number of atoms and the sum total number of electrons. All right, so you don't, essentially you conserve everything that's there. All right, which alcohol would produce carboxylic acid when acidified, when heated with that? All right, the key thing here is that you need to find a primary alcohol to do this with. All right, and this would be an example of that. For this one right here, I'm going to go and skip this one for right now. Certainly the one with the lowest boiling point would be if there was one that had a fewest number of carbons, that would be the one with the lowest boiling point. My guess is that, so this is the answer right here, and the answer that I would give is that the presence of these two methyl groups here, they would think about them as being of this carbon right here. One would be up and one would be coming down. And essentially, when you get good London dispersion forces, what helps you get good London dispersion forces is if you have things in a nice straight chain so that the two neighboring chains can line up really well next to each other. In the presence of these two carbon atoms coming up and below this would disrupt that ability to make so that the neighbors could stack together. Number 6, which could be formed from bromoethane. So essentially, we could use hydroxyl, a hydroxy group, and displace this bromine to make this molecule right here, and then that could be oxidized up to this molecule right here. All right. Although there's not going to be nucleophiles and electrophiles on the quiz, a nucleophile is going to have a lone pair of electrons. So what's one piece of physical evidence for the structure of a benzene ring? All right, and I guess I didn't write the answer down to that. But one piece of evidence is the fact that all the bond lengths are the same. All right, and if you look at the if you look at the typical structure where you got the alternating double bonds and single bonds, you would assume that things would have different lengths, but the thing about benzene is that it's experimentally measured that all those bond lengths are the same. All right, draw the structure of the conjugate base form of benzoic acid. It would be this guy right here. Next question is, why are the C and the O bonds in that conjugate base the same? All right, so essentially, if you looked at it like this, this would be a double bond and this would be a single bond. You would not think those would have the same lengths, but if you draw the electron pairs on these guys, you could draw this resonance structure right here. And whenever you're drawing resonance structures, remember that the true structure is actually kind of an in-between. It's like a hybrid between these two. All right, and that's a way of saying what that shows is that there's an electron pair that's basically smeared between these three atoms. All right, and another way of saying that is that they are delocalized. All right, so you could say that the electrons are delocalized as indicated by the above resonance forms. All right, one thing I failed to mention is to suggest a value for those, and to get the answer to this, look up the bond length of a C double bond O and the bond length of a C single bond O, and just state something that just state that it would be between those two lengths. All right, so these things aren't full, really double bonds. They're not really single bonds. They're somewhere in between. All right. I'm not going to go into the calculation of a pH. You should know how to do that. Would be done with the standard pH equals the negative log of the H3O plus. We cover that in the pH in the acid basis unit. This would be the combustion equation. In this combustion equation, you could see, well, carbon is going to be oxidized. You see like it's gaining oxygens. Oxygen is being reduced because this oxygen here is going to be picking up hydrogens. All right. So this next one is a tough question. So why do you get this apparent dimer? All right. And I've seen this question before on IB exams. So the answer to it is that if you draw two neighboring benzoic acid molecules, all right, so here's one of them, and here's another one of them right here. You can see that they would be set up so that you can get this hydrogen bonding between neighboring molecules, and that's going to be a very sticky interaction. This is, I would just say, it's kind of cozy. All right, so if you think about it, like if you've got two sticks, the more pieces of Velcro you put between them, the more that they're going to want to stick to each other. All right, so since there's two places that these guys want to stick together, they make a very tight species, and that species can actually survive in the conditions of your mass spectrometer, and this combined mass would have 244.26. All right. What could convert benzoic acid to benzyl alcohol? You would need, remember, there's two reducing agents. There's lithium aluminum hydride, but there's also sodium borohydride. All right, and to reduce a carboxylic acid, you need something relatively strong. All right, which is lithium aluminum hydride. All right, sodium borohydride is not nearly as strong. All right, sodium borohydride, if you remember, would reduce a ketone or an aldehyde to an alcohol, but to reduce a benzoic carboxylic acid, you need lithium aluminum hydride. All right. So on this one right here, methyloxyrane. All right. Why is this unstable? Well, if you remember, so focus on these carbons right here. These would be tetrahedral. They've got 4 single bonds coming from them. And remember that the natural bond angle for a tetrahedral carbon is 109.5. So to get this triangle, that would force them to be in a bond angle of 60. All right, and that makes that a strained bond. All right, think of it as it wants to be 109.5, but it's being bent unnaturally into an angle that it doesn't like to be in. All right, so that makes it a little unstable. So two structural isomers. One thing when you look at that structure right there, you would should realize there's a ring in it. All right, and so it would have a total hydrogen deficiency index of 1, and those are the total number of rings and double bonds. So just draw a molecule and just realize it's going to have at least 1 double bond or 1 ring. All right, and here are a couple of examples of things that you could do there. All right, state giving a reason whether this can form cis-trans isomers. No, because to have cis-trans isomers on this, for a ring, you want to have substituents that are either on the same side or opposite sides of the ring. And so in order to have that, you'd have to have a substituent on this carbon right here. All right, in reality, they're both hydrogens, so cis-trans isomers would not be possible. All right, here, okay, we're skipping these for now. All right, classify this as this guy right here. This guy is primary, and that's because the carbon that the bromine is attached to is only attached to one other carbon. All right, and that makes it primary. All right, so remember when you're doing like the primary, tertiary halogenoalkanes or alcohols, it all has to do with how many carbons are attached to the carbon that thing is attached to. It's a little different with primary, secondary, and tertiary amines, which is just the number of carbons that are attached to the nitrogen. All right, and we'll give you an example of that later. All right, we skip these right here. So for this one right here, what are some conditions for reducing ethine? All right, you're going to need hydrogen gas, and you're going to need either a nickel, palladium, or platinum catalyst. There's a couple of other metals that would do this. The IB tends to use nickel as the most common catalyst for this. In reality, I would argue that palladium is the most common catalyst for hydrogenation of vegetable oils. I'm pretty sure they use palladium. I know that whenever I did this in the lab, we would use a palladium catalyst. But either of those would work fine. So when next question is, we hold off on those. We're not doing those. Hold off on those. Some physical evidence that this is incorrect. All right. So again, this would indicate that you've got isolated double and single bonds, but all the measured double and single bonds are the same length. All right. So that's the major one. The answer booklet gave a couple of other options. One being the CC carbon-carbon bond has a bond order of 1.5, which means it's halfway between a double bond and a single bond. All right, but I would stick to this answer right here. I think that's the most obvious one. For this one, order of increasing boiling point. All right, so you want to start off with the lowest boiling point first. Okay, so first we're going to start off with the pure alkane, no hydrogen bonds, no polar bonds. That's the only London dispersion forces is the only force, and that's a relatively weak force. All right, going to this one right here, it's got it. This is an aldehyde. It's got that carbonyl, so it's got a polar bond. All right, that polar bond introduces a little bit of stickiness between the molecules. All right, going to this alcohol right here, this now can hydrogen bond. All right, which is a stickier relationship than just a regular polar bond. And then this guy right here is a carboxylic acid. And the carboxylic acid, the hydrogen bonding is even stronger than in a regular alcohol. All right. In fact, this is the only liquid at room temperature carboxylic acid. All right. Once you add, actually, I might be wrong. So the vast majority of carboxylic acids are going to be solids. All right. Whereas plenty of alcohols are going to be still liquid. All right, what are some functional groups in this molecule? We've got an ester here. This is a carboxylic acid. I don't know why they call it just a carboxyl, but just using a little bit of intuition on this, I would say these two right here. So moving on, this guy right here, you identify the longest chain. 1, that carbon right there. 2, 3, 4. So this is going to be some sort of butane something or other. All right, we're going to, for the carboxylic acids, you're going to consider that the number 1 carbon. And so that methyl group would be on the number 2 carbon, so that's 2-methylbutanoic acid. All right, this is that one about the tertiary nitrogens. Remember, for a tertiary nitrogen, you're just counting the number of carbons that's directly attached to that nitrogen. So tertiary would mean 3 carbons. So this one right here's got 3 groups, 3 alkyl groups coming off of it. 2 of them are methyl groups. 1 of them would be I guess a propyl group. All right. Functional groups here, that's a hydroxyl. This group down here, that's an amide, although sometimes you can call it a carboxamide or carboxamide. But that is not one of the choices. The only choice available is hydroxyl, so the answer would be D. All right. Which one contains a secondary carbon? That means that the carbon would have 2 attached other carbons. So this guy right here would satisfy that. It's got this one right here, but it's also attached to this other carbon right here. All right, which can be reduced. All of these can. All right, so look at all these structures. This could be reduced to the alkane. So this is an alkene. It could be reduced by adding hydrogens to it to make an alkane. This is a carboxylic acid. Those can be reduced to alcohols. And this is an aldehyde that can be reduced to an alcohol. All All right, the general formula here, these are all alkynes, and if you look at these general structures, they would follow that right there. All right, we'll finish this in the next video.